So as we look at this equation, we see, hey, look, the only way we can transfer energy to a system right now is by work. And you may be saying, I don't think that's right. There's other ways we can transfer energy to a system, and you're absolutely 100% correct. We could transfer energy other ways. Okay, so let's just consider our gas in a closed system. So here's our gas, and I'll make this a closed system. Of course, we can transfer energy to that system by work, paddle wheel work, some other kind of work. But you know that we can also transfer energy to systems by heat. Okay, so if we take this and we put a flame down here, and that's an awesome looking flame. That if you have a fire that looks like this, man, you have gotten yourself a deal. Okay, we're transferring heat, energy transfer by heat. Okay, so energy transfer by heat only occurs if there is a temperature difference between the system and the surroundings. So a delta T is required for heat transfer. Okay, now look, I'm writing heat transfer in abbreviations. TXFR, heat transfer, that's how I'm going to say it here. Now, you look at this, you think we're talking about heat. Heat, we're going to call that Q. Second thing today. There's no Q's inside of heat, so why not call heat Q? And when we get down here. People don't like my Q's. They wish I could make a Q like this. Q, I know, I go full out whoosh around all the way around, like that's how I make my Q's. But you know, if that's the worst thing that happened to you this semester, then we have to have a conversation. Okay, heat transfer, just like work, is not going to be a property. Okay, heat transfer is not a property. We cannot find the heat at state 2 minus the heat at state 1 to figure out how much heat has been transferred. There's no such thing as heat, the property of heat. We have to know how we're heating, the method of heating. We have to know that process. That's important. So Q is equal to the integral from 1 to 2 of dq. It is not equal to Q2 minus Q1. It is not equal to that. That's not, you can't work with that. Okay. Heat at a state has absolutely no meaning. Absolutely no meaning at all. In fact, we often have to deal with the heat transfer rate. So Q, heat transfer, is often equal to the integral from 1 to 2 of our heat transfer rate, which is Q dot, just like the rate of work over the time that it is happening. And we must know something about what the equation of Q dot is, and we're going to be working on that in our next lecture to find out what Q dot is. In fact, there's a whole class called heat transfer, which really delves in 16 weeks into that very idea. Okay, but I want to say this one more time, and I'm going to get out my magical rainbow pen to belabor the point. Heat does not equal temperature. Okay, heat does not equal temperature. Don't let yourself believe that or think that. It's not a thing. Okay, and that's the main reason is here. We have something called sensible heat. Okay, and sensible means that we feel it. Okay, and there's also Q latent heat, and this is basically hidden heat. So here's how I like to explain this. Let's just say right now, you after this this lecture segment, you go out and you boil a pot of water. What are you going to do? You're going to go to the tap and you're going to fill up a pot full of tap water, and that tap water, let's just assume that it's 50 degrees Fahrenheit. Okay, we know that water boils at 212 degrees Fahrenheit. So you're going to put it on the stove that you're going to have, and you're going to turn on the stove and you're going to turn on the heat. There's going to be heat transfer from the surroundings to that system. Okay, that's what's happening. And if you were to put your finger into that water, you would feel it increase in temperature. You would sense the increase in temperature. So there would be, as heat is added, temperature goes up, and there's some correlation between there. You say, well, Dr. Wanklund, shouldn't heat be equal to temperature? Why is it? There's a correlation there. Okay. Now, what's going to happen is when the temperature reaches 212, what's going to take place? Well, now you're going to start seeing bubbles forming and boiling is occurring. What is boiling? Boiling is phase change. We're changing from a liquid state to a vapor state. Now, if you were to keep your finger in there, or a thermometer in there would be a better choice now, because it's 212 freaking degrees, you burn your finger off. If you keep a thermometer in there, you would notice that as heat is still added into the system, that temperature is remaining at 212. But what's happening here? Now this heat is hidden. It's hidden for temperature. We can't feel it, but we know it's doing something. What it's doing is it's changing the phase of the substance. So here, heat is not equal to temperature. Temperature is constant. We are now changing the phase. And so that's why it's important to understand the difference between heat and temperature. Okay, so here's some facts about heat that we need to know. Net energy transfer by heat occurs in the direction of decreasing temperature. Okay, so this thing that you might have heard people say, heat rises, heat doesn't rise. Heat goes left and right, it goes down, it goes everywhere. It goes into the direction of decreasing temperature. If you have a warm body and you're on a cold floor, you're going to notice that you're going to feel the heat leaving your body, going into that cold floor, giving your body the sensation of cold, because heat is leaving your body. It's going down. Okay? It can go sideways, it can go any direction. We sometimes get that mistaken feeling that heat has to rise because heated air rises. As my head right now is heating up the particles of air right above it, it's causing those air particles to change its density. That density changes its buoyancy. That buoyancy makes that particle go up as that less dense particle is going to float up because of buoyancy. So that's why I might say that. But heat can go any direction. Okay. Now you might be saying, Dr. Wanklund, with work and the transfer we had a weird sign convention. What is the sign convention for heat? Well, look at this. Heat transfer to a system is positive. Okay. And heat transfer from a system is negative. Okay? Just how nature intended it. If we're adding energy to a system, that's positive. If we're removing energy from a system, that is negative. Okay? So I can say this heat transfer to a system from the surroundings is positive. Heat transfer from a system to the surroundings is negative. That's the way nature intended it. Okay? So don't have to really worry about any thermodynamic sign convention. It's just how we normally would expect it to be. Okay? You might be saying, well, Dr. Wanklund, okay, we got the sign convention, we got some information. What are the units of heat transfer? Well, if you go to our equation that we looked at before, you're going to say, well, it's got to have units of kilojoules or BTUs, just like everything else. Okay, it's going to be the same thing that we're going to be dealing with. If we talk about rates, Q dot, the rate, that's going to be in kilowatts or in BTUs per second. That's maybe what we're going to be dealing with there. Heat. All right. We will pause there and we'll now move on to our next thing where I will unveil the first law of thermodynamics for a closed system.